Chapter 5, slides 33 through 46. Okay, so far we have covered a lot of different ways to show a perspective drawing for a given organic molecule. We can look at the zigzags with their groups hanging off, using wedges and hashes to show that three-dimensional nature. We have shown that you can orient the molecule looking down to carbon atoms and do a Newman projection. For cycloalkanes like cyclohexane, we've been using the chair conformations, which are three-dimensional in nature, and showing, again, the perspective of a given atom as up or down, as it is axial or equatorial. So all we're doing is manipulating the perspective to showcase something. For instance, how low an energy might be, or what conformation a low energy orientation is for a given molecule. There is another type of perspective drawing that you can use that a whole area of chemistry, specifically biochemistry, uses when talking about carbohydrates. So we're not going to be using these too much, which is why I put them in their own section of the notes. So after this section in organic chemistry, you won't really see the Fisher projections moving forward. I won't use them. We're going to be sticking to, the zigzag. That is probably the most prevalent. We will use the Newman projections from time to time, and it is important overall to understand the six-membered rings when you're talking about chair conformations. But I think the most important one that we're going to be using time and time again is more of the zigzag. It's the easiest framework to look at. But I feel compelled as an organic chemist, right? You guys are going to be taking biochemistry, and you're going to come across carbohydrates. They're an important part of biology and biochemistry and organic chemistry as well, but they really are, they have their own way of writing them. And there's pros and cons to writing carbohydrates using Fisher projections. And these are a very specific way. You can see down here, the Fisher projection is shown on the left-hand side. What's weird about the Fisher projection is the fact that all of these very straight bond lines have meaning. The horizontal ones, the ones going in this direction, the horizontal lines, they represent attachment to the carbon as if they're coming out of the page like a hug going towards you, like so. The vertical lines going up and down, these are always going away from you. Okay, so it's like a hunched over carbon with its backbone. And now I always think about Fisher projections like this. So how do you remember? How do you remember that vertical is always going back and horizontal is always going front? This is how I remember it. Okay, we're going to draw a dead fish head. Okay, there's my fish head. It's dead. And I'm going to draw the vertebrae of the fish and his tail. Okay? And understand that the vertebrae, the backbone of the fish, is always going back. It's got the hash lines, okay? And its fins, if they were still attached, are like a hug. Or you could say maybe if it was an animal, the rib cage is going out towards you. So I always think about it by default that if I draw a Fisher projection, get it? If you draw the fish, the up and down vertebrae of the backbone of the fish is going back. So that's what you see in blue here. So this is how I always remember that the vertical is the backbone, which is hashed, just like your backbone. That's my little way of remembering it. Okay, so We can take molecules in their tetrahedral form, the way we like to draw them. This is the way I prefer to draw them, up at the top here with the 2 bonds and then 2 bonds forward and back. So 2 in the plane and 1 forward, 1 back. That's a classic drawing for a tetrahedral. That is my preference. But you can translate these molecules into a Fisher projection. And that's what I want to show you. And I'm first going to start by showing you that there are some advantages to using a Fisher projection. Okay, some of the pros is that it makes determining relationships a lot easier. So relationships are easy. I think they're easier than when you have a zigzag. Because of the way that things are oriented, you'll notice that if R1 and R2 are not the same, you can see that you've got 2 carbons with 4 distinctly different groups off of them. So you can see that it's working towards chirality. You can also look for an internal plane of symmetry very easily, especially if R1 is different than R2, then there's no internal plane. So this is a chiral molecule. Writing its enantiomer has never been easier. Keep the backbone the same, R1 to R2, and literally just swap sides. All the bromines on the right become bromines on the left. You can see that these are mirror images and therefore enantiomeric. The diastereomers, again, notice that 1 carbon next to R1 remains the same from a chiral center perspective, but the other one has changed. The second carbon's bromine went from right to left. So only 1 stereocenter has swapped positions. So you can really see distinctly the diastereomers. It's also easier to determine internal planes of symmetry. And I can give you some examples of that. Let's say we had R1 was the same as R1. You could see that if R1 is the same as R1, there is an internal plane of symmetry right down the center. Everything on the top is perfectly reflected on the bottom. Likewise, if I had R1 with an R1, bromine and bromine. Oh, I should put hydrogens on the other side as well. Notice that here, no matter how I slice it and dice it, I could try a plane going down the center. The bromine doesn't see itself on the other side, so that's not good. What about if I tried to slice it right here and put an internal plane? Nope, the bromines don't see each other. So this molecule is not a meso compound, while this one is a meso compound. It has 2 carbons that are stereocenters, but it has an internal plane of symmetry. So I think that some of the pros to Fisher projections is that it makes relationships easier to see, and it makes internal plane of symmetry a little easier to see without needing to do any rotations. Now, if you ever go and look up, if I can show you here, just as an example, when you look up sugars and you're looking at the differences between glucose and fructose and sucrose, their structures are super similar to one another. And if you were using zigzags, it would be very difficult to decipher between one sugar and another, carbohydrates meaning. So as you can see, when you're looking at carbohydrates in a Fisher projection, because their structures are very similar to one another, it's so much easier to look at them and see the differences and understand which carbohydrate is which if you're using Fisher projections instead of zigzags. So that's one of the benefits. That's another benefit to using Fisher projections purely for carbohydrate chemistry. And that's really when you're going to see them. I'm not going to be using them for run-of-the-mill. Like for the molecules that you're looking at right now with the 2 bromines, I won't use a Fisher projection. I'm going to use a zigzag. but you can understand its merits when you're talking about carbohydrates. Okay, so how do we decipher, how do we use that knowledge and turn, say, a Fisher projection into a regular zigzag? How can we convert between the two perspectives? So that's what I want to train you on. And you won't have to do this other than perhaps on this, exam pertaining to chapter 5. It'll be a one and done because I don't want to harp on it, but it is a good skill to know. So I want you to convert the following Fisher projection into a staggered perspective. The first thing I'm going to have you do is we're going to use what we call the Aquaman Superman helpful tool. Okay, so what I'm going to do is I'm going to stand a person right next to my Fisher projection. This is my superhero. Okay, I'm going to work with two superheroes. He's got his hands on his hips, or her hips. Okay, so notice that I have the head and I have the feet. Okay, now what you're going to do, and it doesn't really matter like what the molecule is doing, but the molecules for Fisher projections always go vertically up and down. They're never written Fisher projections from the side. So you don't really see this ever. People don't do that, okay? They're always going to be up and down. So I like to stand a person right next to it and say, okay, I've got my head and my feet. Okay, so now what I'm going to do is I'm going to count out my carbons from the aldehyde. Carbon 1, 2, 3, 4, 5. This means I have to do a 5-carbon zigzag. 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. Okay, so now what I'm going to do is I numbered the zigzag. I could have numbered them from left to right or right to left. It really doesn't matter. The key here is to be consistent. And that's why I stand my person next to it, okay? Because this is going to matter. So I'm going to draw at carbon 1 the aldehyde. Now the aldehyde carbon doesn't have a stereocenter, so I'm fine drawing just that. The other carbon that doesn't have a stereocenter is carbon 5. Carbon 5 just has an alcohol off of it. It's a CH2. It's got 2 hydrogens on it, so it's not a stereocenter. The ones I have to be most concerned about are carbons 2, 3, and 4. 2, 3, and 4. So what we're going to do is we're going to place Superman up on the top, flying above the molecule, okay? So give yourself some space and make Superman flying above the molecule. Now notice I put the head of Superman at the same position that he's in when he's standing next to the molecule. So I put the head closer to, I didn't draw him in the other direction with this head towards the alcohol. That would be inconsistent, okay? So I drew Superman with his head where it is when he's standing next to it at the alcohol. I'm going to draw Aquaman flying underneath, or swimming underneath, I should say. And my superheroes are always in the same perspective. We need to be consistent. So the head of both superheroes is always as drawn next to the molecule. Okay? Had I decided to draw the aldehyde at the other end, then the superheroes would be facing the other direction. You want to keep the head as you've drawn it in the molecule. Okay. Why am I doing this? Okay, well, remember that first slide I told you about Fisher projections. The horizontal lines are both coming at you, and it's like a hug. It's like it's coming at you with 2 arms, like it's going to go hug you, okay? That's what we're going to focus on. So you've got to imagine that Superman's flying over or Aquaman's flying underneath, okay? So for carbon 2, I've drawn in where those other bonds are. There's a wedge and a hash. And if you look at it from Superman's perspective, okay, so Superman's up here. Okay, Superman's up here. And Aquaman, I'll make him blue. He's under here. Okay, so from Superman's perspective, Superman looks like he's going to be hugged by the substituents or by the bonds off of carbon-2. And he wants to hug it back. He also has a wedge and a hash. Those are his arms, okay? Now, if you think about it, what I want to do is I want to label Superman's vision, okay? His wedge arm, if you're putting your head, try to be Superman. His wedge is what? Is that his left or his right arm? Coming out of the paper with his head in that direction. If you got it correct, then this is his left arm. And the one going into the paper is his right arm. Okay? If I was Aquaman, I would also be wanting to hug this molecule. And so Aquaman's wedge arm, what you're doing is you're underneath looking up. The wedge is now Aquaman's right arm, and the hash is Aquaman's left arm. Okay, so what we're going to do is we're going to say carbon-2 on our Fisher projection has two arms coming out at us. And when I look at this, notice that the OH on carbon-2 is on the right. The hydrogen is on the left. For carbon-3, the OH is on the left and the hydrogen's on the right. So this is the right side of the molecule, and this is the left side of the molecule. I have to keep alternating between Superman and Aquaman as I assign going down my chain. So for carbon-2, okay, carbon-2 is this one. On the right is the OH. So that means my right arm would be touching the OH. My left arm would be touching the hydrogen. Now I'm going to switch to Aquaman. For carbon-3, the OH is on the left. The OH is on the left. That's the hash line, and the hydrogen's on the right. And for carbon-4, I switch to Superman's perspective again. The OH is on the right, and the right for Superman is the hash. Oops, I put an R. It's an OH. The OH is on the right-hand side, so Superman's right is the hash line. And the wedge must be the hydrogen, the left. So then you can erase all of your Supermans and Aquamans, and you will see that this molecule can be written like this. You don't have to put the hydrogens in. This is a lot harder to look at when you're trying to compare carbohydrates, as I mentioned before, which is the pro to using Fisher projections. This takes some practice, and you might not see it right away, but if you use the Aquaman-Superman strategy, it'll be a little easier to convert between these two types of projections. If we add Fisher projections to our repertoire of deciphering and analyzing relationships between atoms, or whether something is chiral or achiral, I'm now giving you a huge practice worksheet to try and figure out whether a molecule is chiral or not. And you can see that I threw in some Fisher projections there to consider as well. Lastly, if a molecule is achiral, it must have a plane of symmetry. So you could draw one plane of symmetry for each achiral molecule as a practice as well. Now, as mentioned in the first slide, there's some odds and ends to tie up here now that we've reached the end of our Chapter 5 material. And I just wanted to consider a few other points relative to stereoisomers, okay? And also summarize what we've learned so far. So isomer flowchart, right? First you need to look at the connectivity. That's the first thing you should do. Always look at your connectivity. Naming helps. 2,2-dimethyl something or other is very different than 2,3-dimethyl something or other. So if things are connected to the same atoms, right? Same formula, same connectivity, you're not considering a constitutional isomer. But if there is a difference in how the connections are made, you don't have to walk down the whole stereoisomer path. You're just like, well, the relationship is constitutional. But if things are connected the same way, but through space there might be a difference, now you have to consider the relationships of enantiomers, diastereomers, or even the same molecule. Sometimes things are drawn very differently, but it's just a different perspective of the same molecule. One could ask, what's the relationship between these two images? And you might look and say, well, everything's connected the same way, but through space, are they the same? Right? And then you'd have to convert your Fisher projection into a regular tetrahedral, and then you'd find out that they are the same. But maybe they were given to you where these two were given to you. One was tetrahedral in perspective, and the other one was a Fisher, and you realize they weren't the same, but they were stereoisomers of one another, perhaps, right? And so you've got to consider that being the same molecule is a possibility. So, reorienting the molecule, changing the perspective, naming the molecule is, again, a surefire way. If there's only one stereocenter and everything is connected the same, and that one stereocenter is S for both, it's the same molecule. It gets a little tedious. You don't want to have to figure out 20 stereocenters. So obviously none of these have 20 stereocenters, but it is a way if you're stuck, if you're like, God, I just can't seem to, make heads or tails of it. Try some sort of naming schematic. Okay. Once you figure out that they're not the same, then you're left with enantiomers and diastereomers. Now, I left out so far, I hadn't talked about it, but we have talked a little bit about alkenes in the cis formation and the trans formation. We've discussed it here and there throughout chapters 1, 2, and 3. But we haven't talked about these two types of isomers relative to one another. What you notice is that you can't interconvert between them. So you can't interconvert between them, right? You cannot rotate around a pi bond. They are set. A cis conformation, where the two groups are on the same side, versus a trans conformation, where the methyl groups in this case are on opposite sides. Those are set molecules. You can't convert them from one to another by twisting. So they're different. Are they enantiomers or are they diastereomers? Well, if you go back to the classic definition, because this is a tough one, right? Technically, neither one has a stereocenter on it. There's no carbon stereocenter. That's tetrahedral with 4 distinctly different groups. The carbons of the double bond are sp2 and only have 3 groups off of them. So it doesn't have a stereocenter. So you wouldn't necessarily think to define their relationship as enantiomer or diastereomer. However, their relationship is diastereomeric. And the reason is because they're not mirror images of one another. And yet they're not superimposable. So it fits the diastereomer definition. Non-superimposable, but are not mirror images of one another. So if you have a cis double bond and a trans double bond, same formula, different orientation through space, these two molecules will have different polarities, different boiling points, different melting points, and so on. Here's some more practice. For each pair, give the relationship between the two compounds. State whether it's a constitutional isomer relationship, enantiomeric, diastereomers, or the same. Lastly, we haven't touched upon stereochemistry as it relates to other atoms. It's important to note that you need the tetrahedral 4-group definition for carbons. But what about other atoms like nitrogen, sulfur, silicon, phosphorus? I mean, nitrogen could have 4 bonds if it was a charged ammonium species, right? Nitrogen with 4 bonds has a positive charge, and then its counter ion is chlorine minus. Well, it is true that nitrogen in this case is chiral and has two stereoisomers, this one and another one, the S and the R. However, the same applies, right? If you have the same groups, B is not considered chiral, and C is not considered chiral. Why is that? I can see why B might not be, right? Because of the two methyl groups are the same. But what about C? I mean, if you treat the methyl, the ethyl, and the hydrogen and the lone pair as four distinctly different groups, why is it that we can't say that the nitrogen has properties of a chiral species? The answer lies in the fact that the lone pair, right there, that lone pair is not a bond, okay? And it exists in an orbital that is a hybrid orbital in this case, right? And so you can see the lone pair in its hybrid orbital. But the problem is that because it's not a bond, it actually is in equilibrium with the inverted amine. So this is called amine inversion. It's like an umbrella. Like, take a look at the, make it a purple umbrella, or actually, I'll do it green. So we've got this umbrella here. Look at all of those groups. Those are the bonds in green. Notice that it inverts like the wind blew, right? And what's happening is it's sort of a tunneling effect. The electrons, I mean, technically, the other side of the lobe of the orbital is on the back side, and the electrons could be in either place, and they're in equilibrium. And these bonds are sort of inverting every single time. They're flipped up, they're flipped down, they're flipped up, they're flipped down. And so this interconversion of an amine prevents the molecule from being optically active. Why? Well, if you ended up treating the lone pair as the most insignificant group, if you labeled it as even lowest priority compared to a hydrogen, because it's not even an atom, so let's give that the lowest priority group. Let's give all of the other ones according to their number, 1, 2, and 3. Notice that if I put the lowest priority group in the back, 1, 2, and 3 is turning the car to the right. Again, I'd have to be underneath looking with the lowest priority group going away from me. After an inversion, after an amine inversion, again, the lowest priority group is down here now, and we're going 1, 2, 3. So 1 to 2 to 3. Now what do you notice about the group? Now it's going to the left, if you're looking at it from the top. So this, if it's flipping back and forth, back and forth, back and forth between them at all times, that means you're going to get a racemic mixture. So this amine inversion causes the nitrogen to be in a racemic mixture. So you don't see amines as having chirality, unless they're in a position where they're ammonium and you have all 4 distinctly different groups. So let's stick to carbon, okay? For all intents and purposes, we are going to stick to carbon chirality when it comes to deciphering the chirality of a molecule. I just want you to be aware that you can get chirality from other atoms, but I'm not going to test you on it. There's also something else to be aware of. Sometimes a molecule will not have a stereocenter, so that chirality equals a stereocenter, at least one stereocenter, plus the no internal symmetry, right? You have to look for that. That is not a hard and fast rule. That's the rule that you should stick to for this course because it'll take you 95+% of the way there. However, as you move forward in your studies, what you'll recognize is that there are other ways that chirality rears its head, okay? And so if you look at this molecule right here, look at every single carbon on the molecule. They're all sp2. They're not sp3. Therefore, How could it possibly be a chiral molecule? Well, this is because of the fact that there would be too much steric hindrance if this molecule was completely flat. And you can see it from the model here. See the two iodines and the two bromines? They're banging into each other. So the most low energy conformation is rotating around the single bond so that you get them offset or scissored to one another. They're offset. And what this does is it puts two of the groups in the plane, and by twisting around that bond, the other very flat benzene ring is now coming at you and going away. So it's almost like a tetrahedral, right? If you have a tetrahedral, you have two bonds in the plane, right? You have the two bonds in the plane, and then you have something coming out at you and something going back. So, and that's all around a central carbon. That's what gives chirality, right? You've got this stereo center there. Now, it's almost like you're creating one massive carbon stereo center with an effect where two substituents are in the plane and then two substituents are out of the plane. So it's almost like you have a bromine, iodine, iodine, bromine. But because the extension is not one carbon, it's a larger entity, you're creating this tetrahedral aspect, but to a broader degree, even though technically there is no sp3 carbon stereo center. And there's some other examples like this. Again, think about a tetrahedral carbon, right? Where you have two bonds that are in the plane and then one coming at you and one going away. I always think of an allene. This is an allene. And allenes, when you draw their orbitals, the pi bond, right? So if you think about the pi bond and the pi bond, right? There's a sigma bond and a pi bond. The sigma bond is just the line that's drawn between the carbons, and the pi bond is being represented as the orbitals. So the red orbitals for one, you can see the red orbitals on the left, are in the Z trajectory because the middle carbon has to be involved in two pi bonds, one in either direction. So if it's involved with the pi bond on the left in the Z direction, it's involved with the pi bond on the right using the Y direction. And the sigma bonds are using the X direction. The orbitals are in the X trajectory. And so the middle carbon is the problem on an allene. So when a carbon is involved in two double bonds, it can't use all Y direction orbitals. It has to use Y direction in one and Z direction in the other. What this does then is it tweaks the orientation by 90 degrees of the groups on the outer carbons. So notice that the outer carbon on carbon 1 on the left has both of its hydrogens relative to the pi bond up and down, but in the plane. In the plane. While carbon 3, farthest to the right, has its Y orbitals up and down, so then its orientation of its hydrogens are back and forward. So it's almost like a stretched out tetrahedral. You can see it down here a little bit easier, where two bonds are in the plane and two bonds are one forward, one back. And for allenes and for these twisted scissored conformations, you actually don't need four distinctly different groups. This twist and having them separated apart allows for chirality of the molecule as a whole. So you will see that in these cases, if you have an allene, you don't need four distinctly different groups. Okay? And this is showing the allene without an asymmetric center, showing that its mirror image is actually technically not superimposable. Here's another example of these hexahelicines. And these helicines are very flat. Every single carbon, again, you'll see is sp2 hybridized. There's no technical chiral center on them. But because there would be, if they were totally flat, there would be too much, there'd be too much steric hindrance here. They would bump into each other. What they do is they scissor again and they orient themselves outside the plane, one of them coming at you, the other one going away, and this too creates a chiral effect for the whole molecule. You see these types of things, right? You guys will go into biochemistry and look at DNA helices, right? And there are 3 different ways of drawing the DNA strand, right? You have A DNA, B DNA. And so how you have right-handed or left-handed helices, even though there's no chiral centers on these amine bases, when you put the whole thing together and you twist the molecule in one direction or another, you end up getting a handedness, and it will be optically active. So I don't want you to come away from stereochemistry thinking that the chirality formula I gave you is the end-all be-all, but it is a great place to start. As you can see, as you get to these larger and larger systems is when you start seeing chirality to a greater extent that offsets from the normal definition I have given you. For the molecules we're going to be using, like I said, the chirality formula that I gave you is going to work 90% of the time or more. I just want you to be aware that it's not hard and fast, and you do have under your belt things like DNA, handedness in DNA, that even though it doesn't fit the chirality formula I gave you, larger molecules will twist and have almost a tertiary structure that lends to overall chirality for a molecule. I leave you with the retrieval cues from chapter 5, as well as critical skills for yourself to make sure that you can perform.